Think about the medication you take. By the time it reaches your hands, this tiny pill looks perfect, clean, precise, and completely uniform. It's the final stop at the end of a very long journey. But that pristine shape is deceiving. Creating a drug is a chaotic process. It requires a complex chain reaction of raw chemicals, solvents, and catalysts, a sequence scientists call a synthetic route. And if you look inside the lab, you quickly see that chemical reactions are rarely 100% efficient. Whenever you combine two substances, you don't just get the molecule you want. You also get leftovers, byproducts, and unwanted impurities. Some of these byproducts are relatively harmless. Others, known as mutagenic impurities, carry a severe risk. Even at microscopic trace levels, these specific chemicals have the potential to damage human DNA. To keep patients safe, regulators require manufacturers to place this entire chemical chain under intense, documented scrutiny. The challenge, however, is figuring out exactly where in that messy supply chain the official oversight actually needs to start. This regulated zone is officially known as Section 3.2 S2.2. Once a chemical enters this window, it is bound by good manufacturing practices. Every step, every test, and every ingredient is heavily documented and controlled. If a manufacturer draws that starting line too late in the process, they create a blind spot. Dangerous impurities generated in the early, unmonitored stages could easily slip through undetected and end up in the final drug. You might think the solution is to start all the way back at the raw earth elements, tracking every single component. But looking at the massive global scale of industrial manufacturing, applying pharmaceutical-grade rules to every basic chemical plant on Earth is logistically impossible. Regulators and scientists have to find a calculated balance. Designating a starting material means drawing a science-driven boundary, one placed exactly early enough to capture all the critical chemical risks without getting lost in the industrial noise. This boundary is guided by an international standard called ICH Q11. It requires manufacturers to map their entire process like a forensic investigator. They must prove exactly where every impurity originates, how it behaves, and how it's eventually removed. This chart illustrates the specific limits where an impurity officially impacts the final drug. You'll see two horizontal lines. The top line sets the safety threshold for standard impurities. The much lower line dictates the strict limit for mutagenic impurities. Notice how much lower that second line sets. Because mutagenic impurities carry a severe risk to DNA, the tolerance for them is incredibly tight. A much smaller amount triggers a regulatory response. If any manufacturing step generates an impurity that crosses its designated limit, that specific stage of the chemical synthesis must be captured inside the regulated oversight window. Let's look at how this plays out in practice with a hypothetical manufacturing process. Here, a manufacturer creates a drug through a sequential chain, starting with chemical A, transforming it into B, then C, then D, and finally synthesizing the drug itself. A manufacturer might submit a plan drawing the regulatory starting line at chemical D. They argue that applying intense oversight to just this final transformation is enough to ensure safety. But when scientists reverse engineer the final product, testing reveals two dangerous impurities crossing the impact threshold. By tracing the chemical forensics backward, they find both of these flaws actually originate at step C. Because these impacting impurities originate outside the proposed boundary, regulators reject chemical D as a starting material. The regulatory window must be expanded backward to capture step C. The logic is straightforward. You cannot safely begin monitoring a drug's creation after a critical, unpurged chemical threat has already been introduced into the chain. Some chemical flaws are even more stubborn. Take a persistent impurity, a structural issue, like the wrong molecular orientation, that appears right at the beginning of the chain at chemical A. Unlike other byproducts that get washed away, this specific flaw hitchhikes through every subsequent reaction. It survives the transitions through B, C, and D, landing squarely in the final drug. Because this persistent threat travels the entire length of the process, manufacturers must push the starting line all the way back to chemical A. The whole route must be regulated to control it. There is one main exception to these strict traceback rules. If the chemical in question is a commercially available commodity, something widely sold for non-pharmaceutical uses, like industrial manufacturing, its inherent risk is considered lower and requires less justification to be used as a starting material. Outside of that specific exception, the unique chemical history and behavioral traits of the substance itself dictate exactly how much regulatory scrutiny is required. When you zoom out from the abstract flowcharts and look at thousands of pills moving down the line, the stakes become incredibly real. Defining a starting material requires a complete forensic map of the chemical chain reaction. By aggressively tracing impurities back to the exact moment they form, the ICH Q11 guidelines guarantee that every critical transformation happens directly under a regulatory spotlight. Testing a finished pill confirms its current state, but permanent safety is built by mastering and controlling every chemical transformation in its history.